Hello, this is Cliff Jordan, and you're now watching part 5 of our series on linear regressions. This is a data science series dedicated to linear regressions. There's going to be other series going to be dedicated to other algorithms like logistic regression and data transformation, etc., etc. This is all dedicated to linear regression. In this, we're actually manually using Excel, but manually doing a linear regression to help you understand how linear regression is actually calculated and also understand all the accuracy measurements behind it. We've already done all the hard work as far as the linear regression in our previous 4 videos, but what we're going to do now is focus on the accuracy measurements and how to calculate the accuracy measurements for the linear regression. The first accuracy measurements we're going to talk about is known as SSE, sum of squared error. Now, at the end of our last video, what we did is we calculated the error by just taking the predicted, the y-hat, that's this value right here, and we subtracted the actual, okay, and that gives us the error. What we're going to do now is we're simply going to square that, and then after we square that, we're going to sum it up across all the rows, okay? And this total sum will be what we call the sum of the squared error. It makes sense. It's in the words. It's exactly what it is. Okay. Now, in this particular case, it is definitely lower the better. The lower this value is, the less error you have. It's not subjective. It is the truth. The lower the better. So you want your sum squared error to be as low as possible. Is there any set value? No. This all depends on your data, and so the only way that you could compare your squared error with somebody else's squared error is if they had the same data and trying to do the same things, and then you could look at that. But if I'm working on one type of model, such as this coupon versus purchase date, and someone else is doing a model on something completely different, like the iris width in the eyeball or something like that, that is completely different data. SSE would be completely different. Okay, so SSE is really more for comparing one model or one attempt at modeling for a particular outcome against another similar model using the same data. That said, let's go to the spreadsheet, which is where all the magic happens. So here we're at the spreadsheet. So here's my SSE. Before I can calculate the SSE, I have to square my error, which is fairly straightforward. I just take this value here, square it, which is what the formula does. So let me go ahead and uncover this. Yeah, all right. Let me highlight all these, and there we go. So there's a squared error. Now, the cool thing about squaring is it gets rid of all these negatives, and then it allows us to actually add these up and get some sort of idea of error. So now we're going to add these up, sum it up, and that's done in this particular formula. So it's the sum of everything in that column. That said, let's uncover the answer. And it's 2,451, which doesn't really mean much. Doesn't mean much at all. In fact, if I hit F9 a few times, which regenerates new data, you'll notice that it's going to bounce around. But like I said, if you're comparing one model with the same data to another model with the same data, whichever of those two models has the lowest SSE is probably the better model. Not probably, it is the better model. Okay. The next thing that we're going to look at is called MSE. And MSE stands for, let's see, what does it stand for? Mean squared error. So basically you take the error, the SSE that you have, and now we're going to divide it by the total number of rows that we have. Except we're not going to divide it by the total number of rows, we're going to divide it by the total number of degrees of freedom, which you remember as dependent on the number of rows and the number of variables. So as we divide it by the degrees of freedom, this kind of gives us a error per degree of freedom, which is highly correlated to the error to the degree for each row. So that's fairly straightforward. So let's go back to our spreadsheet, and there it is. So here we're going to divide K5 by I4, which is our degrees of freedom. K5 is the SSE, and so that's straightforward. Boom. Uncover it. We divide it by 82, and this is what we get. So our average or our mean squared error, let me take this out, all these bits of precision, is 42.97. Remember, this is still a squared value because we use squared error here, right? So it's only natural for you to say, well, let's just take the square root of that. And that's what we do on this next step. And this is called root mean squared, which is right here. Basically, you take that MSE and you take the square root of that, okay? And again, lower the better. It's nothing big here. It's fairly straightforward. So let's go back to our spreadsheet and look at that, and there it is. And sure enough, it's the square root of the mean squared error. So let's uncover that, and that is, and let me take away all that precision, 6.55. Okay, which, when you think about it, this is probably the closest to what we would call a standard deviation for the prediction. So in other words, the y itself has its standard deviation, okay? And where was that standard deviation of y? Right here, okay? Now, the RMSE also is known as the standard error, or residual standard error, is also could be considered a standard deviation for the prediction. Okay, that's important to understand. So, with that in common, or with that understanding, we can now continue. So, in the RMSE, same thing like we said before for the MSE and the SSE, the lower the better. Okay, the next thing we're going to calculate is known as the F value. Now, the F value, let's go see what we got over here. But F value is the MSE, which is that this right here, the mean squared error, divided by the SSR, which is the sum of squared errors. Excuse me. Hold on here. Let me go back. What does SSR mean? There it is. Residual sum of squares. Okay. Keep me honest there. This is known, the F value is known as the explained variance, which is the MSE. We can explain that. That is the variance that comes from the prediction, okay, to the actual. Divided by the unexplained error variance, which we had talked about before in our previous video, which is the SSR. All right. Typically, for F value, the lower this is, the better. Okay. And let me go back to the spreadsheet. Let's take this, and sure enough, this is K6, which is this MSE divided by the SSR. Let's go ahead and uncover it, and there it is, 0.0004. Now, let's do an experiment. Typically, our model, if the data has less variance, the model is better, okay? Right now, I've got very little variance. I've got, on the variance when I generate it, it only has a variance of 10. And that's why when we saw the scatter plot, we have very little variance here. What I'm going to do is I'm going to increase this variance. And I want to see what happens to the F value when I increase the variance. Because when I increase the variance, the model is worse. It's not going to be that good. But how's that going to impact the F value? So let's do this little experiment. So right now it is 0.004. Let me just copy this. Copy and put it right here. Put the value. All right. So now what I'm going to do is I'm going to increase over here the variance from 10 to, let's put it at 60. Okay, which is considerably more variance. And then I'm going to hit F9. So it just generated a whole new set of data, and let's see what happened. Well, sure enough, the F value goes up. If I go back to the scatter plot, you can now see there's a whole lot more variance in it. Notice that R squared went from 0.69 all the way down to 0.11. So that tells me that this model, yeah, it's a trend line, but it doesn't explain the data as well, okay? And because of that, the F value went up. So we've just confirmed that the lower the F value, the better, okay? And so that's what I wanted to show here. All right, that said, what we're going to do is we're going to go ahead and end this, and we're going to end this right now. And what we're going to talk about in the next video is the following. What we've talked about, all these measurements of error here, have been based upon the predicted value of the predicted purchase amount versus the actual, okay? And so we've created all these measurements based on that error itself. Now, when you think about it, what were we trying to predict? What were we trying to gain from the linear regression? We were trying to gain a couple of things. One, I want to be able to use the output of the linear regression to make predictions about how much they're going to purchase. And I do that through the y equals mx plus b. Here's the m, here's the b. But I also wanted to get a feel for the sensitivity of the patron. And the sensitivity is nothing more than the m, the slope. Remember, what this is how much money, for every dollar of coupon I give the patron, how much is he going to give me back in return? And so what I've been doing is by calculating the m, I'm better understanding what's inside this guy's head. And remember, here's what's inside of his head right here, a 3. That's his true sensitivity, and this is my estimate based on his behavior. So his behavior is indicating that his sensitivity is around 3.6. So there's a difference between the estimation of the sensitivity and the real sensitivity. Then that kind of makes you think, well, then there's an error in the sensitivity measurement, or the error in the slope that we measured, okay? Well, if there's an error in the slope, then there should be some sort of error measurements associated with the slope, or with the slope of, in this case, with the independent variable. Now, remember this y equals mx plus b, okay? That m is the slope, but it is also the coefficient to the x variable. And this is very important. So m, we call it a slope. In reality, it is a slope. If I had 2 or 3 different variables, well, instead of calling it a slope, we would just refer to it as a coefficient to the variable. And in reality, if I got 2 variables, the 2 m's are slopes in the ordinate directions of each of the variables. Okay, that's important to think. If you could think, if I got 3 variables, it's a three-dimensional. It's a three-dimensional cube. If it's 2, it's like a a surface. Okay. That said, let's go back to the plot. There is an error between what I estimated the slope to be and what the actual slope to be is. And so now what we need to do is create some error measurements associated with our estimation of the slope. And believe it or not, we're going to do the same thing for the y-intercept. So here's the y-intercept. We're estimating it's 96. In reality, it's 100. So now we need to come up with some estimates based on that. But here's the key. Remember, all of these are in the mind of the patron. I don't know what they really are. Okay? I don't know what the true y-intercept should be. I don't know what the true sensitivity should be. All I know is what I've estimated based upon the data. So we're going to have to come up with error measurements that do not take into account what is inside this guy's head that I have no access to. And that's the beauty of these measurements that we're going to be coming up with in the next video, which starts now.